just wanted to make a quick video showing how I'm going to be controlling the heater of the machine with my microcontroller. I'm going to be using a PID system, and here we go. So on the left here you can see my experimental setup, so it's not quite fancy. I just have the STM32 connected to the computer, a couple jumper wires, alligator clips, power supply at the top right, etc. The circuit diagram is at the top right as well, kind of just shows what's going on. We got the STM32, the ADC connected to the resistor of the thermistor, the RSAT that we discussed the last video with the 3.3 volts from that system. Then we have PWM going out to the FET module that's connected to the power supply as the source, and then it just goes out to the heater, which has a 4 ohms heater. So there's a couple different ways that I can control the heater. First of all, there's just on-off. So like with the PWM signal, you can have 0 or the max. So it's like 0 volts or the max voltage. You can also have proportional control, which is controlling the output based on the error of something that you're measuring. You can have integral consideration and derivative consideration, which we'll get into later in this video. Often though, these systems, a big problem is that either like the heater overshoots or undershoots, or it has an unstable output, so it'll just keep alternating between up and down, and it won't really stay at its stable temperature. So as we just discussed, the on-off approach is just where if the temperature is lower than the desired temperature, then we want the heater on. If the temperature is above the desired temperature, then we just want the heater off. So that's like the most basic you can really get it. With the proportional system, you would have the error being measured between the desired temperature and the actual temperature, and then you would have the PWM output as this error times a constant. So this would just ensure that if you have a large error, then it would be putting out more PWM signal. If you have a small error, then it would be putting out a smaller PWM signal. So here's a little example I made in Python. It's just kind of like a car going to a goal here. You can see that the on and off overshoots. So as soon as the car sees that the goal is to the left of the car, it'll turn left and then start going left. And then once it sees it's to the right of the car, it'll turn right and start going right. So this is the issue that is with the on-off system. It's not very controlling of the steering, whereas the proportional system kind of actually measures the error and then it increments that in the system itself. So as you can see, it kind of corrects itself as it goes. It doesn't just immediately go to the maximum or the minimum. It corrects the steering as it goes, dependent on the error it sees. Now that we kind of understand the difference between the on-off or the proportional system, we can talk about derivative and integral. So derivative, an example of this is when if you blow on the nozzle, then it cools down quickly from that air. So we have the derivative consideration here for the reason that when there's sudden changes in the system, such as blowing on it, or if a strong gust comes through and changes the system quickly. So for the integral, it's kind of the opposite of this. So an example of this is if the cold draft is always present in the system that you didn't really consider when you were making the PID. So the integral can actually sense that the system is below optimal or above optimal, and then within a couple cycles of getting data, it'll correct for this. So now that we've talked about the on-off, proportional, derivative, and integral, we can kind of look at how this is implemented. So for basic PWM value, we have a PID underscore P, which is the variable for the multiplier for the proportional, and all we do here is get the error seen in the values, which is calculated by the current value minus the value that we want. So that's the error 0 here, and when I'm talking about error, I'm just gonna like theorize this as an array where 0 is the current, minus 1 is the previous, minus 2 is the previous to that, and etc. So we have PID P times our error of current, and then we have plus or minus PID D So this is the derivative, so all we do here is just subtract the previous error from our error now. So we're seeing if we're getting closer to the value or farther away from the value. And then to that we add or subtract PID I times the previous error, previous to that, previous to that, previous to that. So the reason we do this is because we want an accumulating error for the integral, so we can see if our error is getting closer or farther away. So all of these magnitudes added together makes up the PWM value. And all of these PID values are found through testing. So usually you start out with I and D as 0, and then you can find the optimal proportional variable, and then you can start incrementing D and then I to figure out what your system works best. And this is really dependent on each system specifically. So if you have something set up in even as different as one room versus the other, if there's a different temperature gradient or wind in one room versus the other, it'll actually determine different PID values for these. So for the system that I'll be using, I decided to go with a PID system plus C. I don't really know what it would be called, but so I want the proportional and the derivative, so in case anything happens where the heater goes down very quickly, then it can correct itself and not overshoot or undershoot. And proportional, of course, because that has better control than just the on-off system. So for the plus C, I just added it so there would be constant PWM to dampen the system. So when the PWM equals C, it cools down a lot faster than when PWM equals 0, for obviously C is greater than 0. So it'll just help keep the system a little bit more stable and dampen it. And as you can see, the code below, it kind of gives a little bit of insight as to what's actually going on. It's not too crazy fancy. You also don't have to really consider the time when you do the derivative, because technically for something like derivative, you would be actually multiplying or dividing by a number to get it into like degrees per second, but since we're multiplying by a constant PID underscore D, when you're actually tuning the system, it will actually not make much of a difference. So as long as you have your PID underscore D a correct value, then it doesn't really matter. You can also see that I capped off the ADC as from going from 0 to 255 because you can't have the ADC value lower than 0. And for my ADC, I have an 8-bit ADC that I implemented, so the max will just be 255. So here's just a quick video of the PID controller heating up. I just want you to note that at the lower temperatures you can see that it's very up and down. The temperature readings aren't as accurate, and then as we get to a higher temperature it really evens out and gets a lot smoother. This is purely due to the fact that we made our system set specifically for the resistors that we chose to make it smoother during higher temperatures. If you don't know about that, watch the previous video and it'll give an explanation. Additionally, this is sped up quite a bit, so I believe this is 5 times the speed. I just did a time lapse on my phone, so. As we reach our desired temperature here, 150°C, it starts to slow down a little bit, and you can see it dip down a little, but it'll eventually settle at around 149, which is pretty good. I can still do a little bit of tuning, but the PID system seems to be working pretty well. Here's just a small comparison video of the on-off system in comparison to just the P system. So as before, on-off is just considering the PWM as either 0 or 255, which is the max, and then the P system generates the PWM with consideration of an error times a constant. So as we can see here, the on-off system actually has a lower low value, as you can see on the bottom left of the screen, and then a higher high value, as you can see on the top left of the screen, compared to the P system. So we can see that this isn't as effective. They're actually both quite ineffective at doing this temperature controlling, but you can just kind of see a little bit of a difference as how the PID system is a little bit better. Here's a test done between the P and the PID system. I added a +C constant to both PWMs to keep it from oscillating as much. As we can see here, the experiment is when I blow on the extruder aluminum profile and it goes down. The PID system immediately goes at 255 and then it makes it go up faster. The PID system has a controllability of the derivative, so it doesn't go up as fast and it reaches the goal at a slower rate, but it doesn't overshoot as much as the PID system does. And finally, we have our end result. So this is what I'll be using for the most part for this project. I might tweak the PID values a little bit, but as you can see, it's quite consistent with the temperature. It's not exactly 150, but it's around 149. I didn't go to the full 220C, which is probably what I'm going to be doing to melt the PET, but this should be sufficient testing for now, and then I'll tune it in later. Thank you for watching, and I hope this helped.